Good day. Welcome to the presentation of Silicon to Screen Hardware Accelerated Graphics on T2G using Zephyr. This presentation mainly covers how we manage to implement an automotive instrument cluster using Zephyr on the CYT4DN SoC. This demo is a two-part demo. One mainly covers on the automotive instrument cluster and the other covers live camera feed over Gigabit Ethernet. Now, this is the first part of the demo, which is the automotive instrument cluster. As you can see over here, there are three primary ECUs. One is the cluster ECU, the other is the rear camera ECU, and the other is the vehicle simulator ECU. So, moving on to the part of what each of these ECUs do. The vehicle simulator ECU is a CYT2BL SoC, which sends live CAN signals over the CAN bus, and this CYT2BL SoC simulates the CAN data of accelerometer, odometer, gear readings, turn signals, and all the necessary signals that we get on the instrument cluster. Instead of having multiple ECUs over here, we have managed to simulate a single ECU to send all these data over CAN. This primary ECU over here is powered by the CYT4DN hardware, which is the primary instrument cluster ECU. This ECU is responsible for rendering the cluster plus showing the reverse camera onto the display. The other is the rear camera ECU, which is also powered by the CYT4DN SoC, which is responsible for capturing and streaming the video over Gigabit Ethernet to the central cluster ECU. As you can see, the cluster ECU is connected to the monitor via HDMI. This HDMI monitor can be 720 pixels resolution at max, since the CYT4DN SoC is capable of displaying graphics at the 720 pixels resolution at 30 frames per second. As you can see, the camera is connected to the rear camera ECU over the MIPI CSI-2 interface. As you can see here, the camera we've used here is the 0V5640 sensor, which is interfaced to the rear camera ECU via the MIPI CSI-2 interface. The primary reason we've used this 0V5640 sensor is that this has an inbuilt image sensing and processing unit, which makes it easier for the CYT4DN hardware, since it doesn't need to do any image processing for the live camera feed. Instead, the camera does everything on its own. As you can see, this tag represents the entire software that is running on the display ECU, and the dark blue ones are the ones that we have developed here at Linumiz. So, the display ECU's primary goal is to receive and render and display graphics onto the HDMI monitor that we saw on the previous slide. The display app renders the cluster menu from CAN signals and also shows the incoming video. That is the primary objective of the display application. This display application is powered by the LVGL stack and also consists of necessary threads to showcase and receive CAN data. As you can see, these are the primary subsystems that we have used in order to implement this display ECU. Primary ones being the subsystems which are responsible for the graphics plus display stack. The primary one goes to LVGL. LVGL is the light and versatile graphics library, which is used by the developers in order to create widgets and styles to turn it into draw tasks. Okay, primarily LVGL works on the software renderer, which is the CPU, but instead we've managed to make it use the graphics 2D unit on the CYT4DN SoC by the provision of draw units, which is provided by the LVGL version 9. LVGL version 9 provides draw units for the developers to use in order to implement draw units, which can be specialized units that can be utilized by specific APIs of the middleware of each graphics units. In our case, it is the middleware of Graphics 2D, which is provided by Infineon. So this primary middleware consists of all the necessary APIs in order to control the GPU, in order to draw and vectorize any necessary graphics and images using the GFX2D unit. So what happens here is, whatever LVGL API that the display app calls on to gets converted into graphics 2D draw units, which would in turn call the graphics 2D middleware over here. And this is the primary network part of the display ECU, which consists of BST sockets in order to get UDP datagrams. And the network stack over here is UDP plus IPv4 plus L2 Ethernet frames. So what we have done here is we have managed to get the live camera feed over Gigabit Ethernet via these network stack of Zephyr, and this two layers over here comprises of the core Zephyr kernel area, which is the Zephyr's core kernel services, the scheduler, timers, device driver model, and everything. And this over here consists of the drivers that we have developed over here in order to make this application possible. Over here we have the display drivers, which can be divided into three drivers. One is for the graphics engine to bring up the graphics engine, and also the other driver is the video SS encoder driver, which is responsible for driving the display controller of this CYT4DN SoC. The IT6263 bridge driver consists of the LVDS-to-HDMI bridge that is on board in order to convert LVDS signals to HDMI signals. The GEM Ethernet driver is the cadence Ethernet driver that we've used to provide Ethernet capabilities to this application. The AXI DMAC driver is a memory to memory DMA driver, which gets chunks from the networking stack over here and copies it onto the VRAM over here. So this entire thing happens without any CPU intervention. The graphics generated is primarily done by the GPU due to the help of GFX middleware and LVGL, and the necessary display driver and the display controller part is generally driven out by this entire stack over here. This is done without the intervention of CPU due to the AXI DMAC driver over here. This part over here is the T2G CYT4DN SoC, which consists of the GFX2D engine and the video scan out, which is the display controller driver, and the video RAM, which is 4 MB in the CYT4DN hardware we have, and the GEM MAC plus AXI DMA IPs over here. This IT6263 to HDMI monitor is the I2C bridge which converts LVDS to HDMI. This is not part of the SoC itself. This IT623 to HDMI monitor converts LVDS to HDMI signals, and this is not part of the SoC. Instead, it is present off chip and on board. This Ethernet 5 over here is capable of Gigabit Ethernet, which is the primary reason we have managed to accomplish live camera feed over two ECUs via the Gigabit Ethernet over here. So as you can see, this entire stack over here represents the display ECU, which is responsible for getting the camera data and also showing necessarily the instrument cluster. This stack over here represents the entire software that is running on the rear camera ECU. The rear camera ECU is responsible for capturing and streaming live camera feed over Gigabit Ethernet. So what happens here is we have managed to implement a capture application which captures each frame and streams it over to the network via the UDP and IP stack, or even the TCP IP stack. We have managed to use the UDP stack over here, and this is mainly possible due to the Zephyr video API, which provides the Zephyr device model for cameras, and the GFX2D graphics middleware here is needed because the live capture unit is part of the graphics unit in the CYT4DN SoC, and the middleware over here makes it possible for the capture unit to work. And once this live camera feed is captured, it is sent onto the network using the Zephyr's UDP IP stack. This platform over here consists of Zephyr's core kernel services and the drivers that we have implemented to make this rear camera ECU feed possible. The CSI-2 driver is a Zephyr video driver that we have used to make the MIPI CSI-2 plus the capture unit functional. This CSI-2 driver captures whatever live camera feed is captured onto the capture unit, and once that is done, we use the Ethernet driver as mentioned in the network stack above. This GEM Ethernet driver is also part of the same cadence IP that we have seen in the display controller ECU. This GEM Ethernet driver makes it possible for us to send live camera feed over the Gigabit Ethernet. As mentioned before, this is the T2G CYT4DN SoC, which consists of the MIPI CSI-2 receiver, which makes it possible for cameras to be interfaced and the live feed to be captured. And the capture unit is responsible for actually getting the camera feed data, and it uses a DMA to send frames to VRAM. And the VRAM over here is 4 megabytes, which is non-cacheable. And the cadence Ethernet over here is the Gigabit Ethernet. And the 0V5640 image sensor is not something that is part of the SoC. We have managed to interface 0V5640 via external MIPI CSI-2 interface, and which streams the live camera feed over to the display ECU. This demo showcases an automotive instrument cluster powered by Zephyr Autos. Zephyr is an open source real-time operating system maintained under the Linux Foundation. This demo can be split into two parts: the central primary instrument cluster display and the real-time camera feed over Gigabit Ethernet. So regarding the hardware classification, the hardware can be split into two types. One is the cluster device over here, and the other is the body entry controller kit. So the cluster device over here is powered by the CYT4DN SoC, and the body controller kit over here is powered by the CYT2BL SoC. Coming back to the CYT4DN SoC, the CYT4DN SoC consists of a 2D graphics unit and display controller, and it also has a Gigabit Ethernet over here, and also Bosch's MCAN, which makes it perfect for this entire instrument cluster demo. This demo is part of an ongoing collaboration between Linumiz and Infineon. Now moving on to the first part of the demo, which is the primary instrument cluster over here. The primary instrument cluster over here is powered by Zephyr Autos and also an external module called LVGL, which stands for Light and Versatile Graphics Library. This instrument cluster over here is 720 pixels and is running at 30 frames per second. The CYT4DN SoC over here has a 2D graphics unit along with a display controller, which is capable of outputting LVDS. As you can see here, the display is connected via HDMI. If the SoC outputs LVDS, how do we get HDMI here? This is achieved by the LVDS to HDMI bridge over here, which is powered by the onboard I2C. The CYT4DN over here is capable of displaying graphical image generated. The GPU consists of two things. One is the blit engine and the other is the vector engine. The graphics over here is constructed by both these engines combined together, and with the help of a command sequencer which does the heavy lifting instead of the CPU in order to have this smooth graphical interface without the intervention of CPU. Now moving on to the data shown over in the cluster. This data over here is not fabricated by this display controller unit over here. Instead, it is simulated by the scan simulator, which is the CYT2BL SoC over here. Instead of having multiple ECUs to showcase the data over here, what we have done here is to simulate the CAN data via a single ECU, and this ECU over here sends the accelerometer, odometer and the gear and other controls of this entire demo via CAN. So for the demonstration purpose, we have just had one single control from the CYT2BL, which is the switching on and switching off of turn signals and the hazard lights. So this hazard lights and the turn signals that show over in the cluster is primarily sent by the CYT2BL SoC over here. Now moving on to the second part of the demo, which is the live camera feed over Gigabit Ethernet. The live camera feed over Gigabit Ethernet is also done by the CYT4DN SoC over here, which is capable of interfacing a 720p camera via the MIPI CSI interface. The transmitting of live camera feed over Gigabit Ethernet is capable due to Zephyr's TCP/IP stack and also the UDP stack. Now to showcase the live camera feed over Gigabit Ethernet, we'll press user 2 from the CAN simulator over here. And as you can see, the camera feed is very smooth and responsive. This is mainly achieved by the Gigabit Ethernet. The gigabit speeds make it easier to transmit live camera feed over to another ECU. This is how we have managed to implement hardware accelerated graphics on the CYT4DN hardware using Zephyr and LVGL. If you have any questions, please contact at linumiz.com. Thank you.